Welcome back to this course on machine learning using Python programming. In the previous lecture, we have seen in case of simple linear regression how we can find the model's parameters, and then we have seen there are most popular two methods, normal method and gradient descent method. So, in the normal method we have seen in the last lecture, and in this lecture we will see gradient descent method in detail. So, gradient descent method, it utilizes three properties that we discussed earlier in the previous lecture of the parabola curve that we have for the cost function, that is nothing but sum of squares of predicted errors. So, we can say here this curve has only one minima, and using the slope and direction of this slope we can find the values of parameters for which cost function value is minimum. So, gradient descent, as we have discussed already, it can be applied in many other machine learning techniques where we are trying to find parameter values in different steps, and we are trying to minimize some cost function. So, we generally interpret as we are trying to find out those parameter values such that the cost function is minimum. And what we do in this case, we for each and every training instances we use a model, and then we find the error, and then we try to update model parameters based on this error, and again the newly updated model is used for the next instance to predict its dependent variable value, and again we calculate the error, and based on this error we will try to update parameters values, and in that way we will again get the updated model, and then this updated model will be used for the next training instance. These steps goes on until it is satisfying some termination criteria. So, we need to define some termination criteria like number of steps, or if this error is less than some threshold value, or there are many other termination criteria that we can talk about. So, this is the basic idea behind gradient descent. So, here we can see here, this is the model, and it is in this case this model is written in case of multiple linear regression model. So, we are assuming that there are more than one independent variables. So, first independent variable is x naught, then second independent variable is x1, and nth independent variable is, so basically n plus 1th independent variable is xn, and dependent variable is yp or h naught. So, we are representing our model using this equation, and now what is the objective here? Our objective is to learn values of these parameters. So, in the previous lectures we used the term b0 and b1 to represent parameter values, parameters of the model. Here the same thing we are representing using theta naught, theta 1 up to theta n. So, one can represent it as b naught, b1 or up to bn. So, this is only the representation difference in notations otherwise both are same. So, theta naught, theta 1 up to theta n are nothing but model parameters, and we are already assuming there is a linear relationship between yp and these independent variables x naught, x1 up to xn. So, now our objective is to learn these parameters values from the data set, and then we will say that this is the actual relationship between dependent and independent variables. So, in this case we can define this cost function. So, this is nothing but sum of squared prediction errors. So, this is prediction error for the ith instance. So, h of xi is nothing but predicted value for x, and y dash is the actual value for x. So, x is nothing but, we can say that ith, we are talking about ith instance, and for ith instance x is the set of independent variables. So, this is nothing but x naught, x1 up to xn, and so we can say that h of xi is representing the value of dependent variable for this instance. So, that is suppose y. So, actual instance, actual dependent variable value for this instance was yi, and the predicted value is h of xi. So, difference between these two is the error, and then we are taking some square of this error, and we are taking sum over all the instances. So, this is called as the sum of squared error, sum of squared prediction error, and then we are taking average of this. So, we are dividing it by m. So, we are assuming there are m number of instances. So, that is why we are dividing it by m, and we are using here to just for mathematical proofs. So, it is easy to mathematically we are doing something. So, we sometimes it is easy if we use here 2. So, that is why 2 is again added. So, but this is now the cost function or total error that we want to minimize. So, now we can say using gradient descent method, we will check how to find these parameter values such that this cost function is minimum. Here in gradient descent method, what we do, we take we find out the slope of that curve that we discussed in the last lecture. So, generally we have seen that if these are the parameters of the model and this is the cost function. So, we have seen that we get this type of parabola. So, here our objective is to find out that minimum, we have to find out those values of parameters such that the cost function is minimum. So, this when we find out the slope. So, based on the slope value and direction, we can check on which side of minima we are and how farther we are from this minima. So, if slope value is large, we are farther from this minima. If slope value is close to 0, we are close to this minima. So, what we do to get the slope, we take derivative of the cost function with respect to each parameters. So, theta naught, theta 1, theta 2 up to theta n. So, we have n plus 1 parameters. So, or these are called as coefficients. So, we will take derivative of the cost function with respect to all these parameters, and that is written here, you see. So, when we will take derivative of cost function with respect to theta j. So, this is written for the jth parameter, but it will be done for each and every parameter, and then when we will take derivation, we will get this expression. So, in general, if we talk about simple linear regression, so there will be only two parameters. In case of simple linear regression, we have seen that our model is y is equal to b naught plus b1 x. So, or it is also called as c plus, we can write it as c plus mx. So, there are two parameters here, m and c. So, first we will differentiate it with respect to one of these parameters, suppose m, and then we will take gradient with respect to c. So, these two equations we will get, and then what we do, we will update these parameters using this equation theta j is equal to theta j minus alpha delta j upon delta theta j. So, what is this alpha? Alpha is nothing but the learning rate. Learning rate gives us the idea how fast we are changing the value of theta. So, if alpha is large, in that case we are changing the value of theta j in one step we are changing it very fast in each and every step. If the value of alpha is low, in that case we are changing the value of theta very slowly in each and every step. So, this alpha is called as the learning rate, and that is why if we want to learn fast the values of parameters, we will make alpha, the value of alpha large. Otherwise, if we want to learn these parameters values slowly, in that case we will make the value of alpha low. And then so these are the previous value of parameter. We are updating value of parameter by this equation theta j minus alpha into this slope delta j upon delta theta j. So, that we calculated here. So, we differentiated, we have taken the derivative of cost function with respect to each parameter. So, when we are updating one parameter, so we will use here derivative of j with respect to that parameter, and then we can say that derivative of j with respect to theta j, we can take this for all the instances. So, here you can see that this equation that we are getting. So, simply we put this value, right hand side value here. So, this is delta j means derivative of j with respect to theta j that we have that we got from there. So, now the idea of in gradient descent method for obtaining the best values of parameters. So, I hope you are understanding what is the best values of parameters. Best values of parameters are nothing but those values for which value of cost function is minimum. So, how we are doing? We will randomly initialize these parameters theta naught, theta 1 up to theta n. So, initially we will randomly take some values of these parameters, and then we will calculate derivative of this function with respect to these parameters, and we will update it. We will update all these values. So, you will, when we will get the new updated parameter values, so it means your model is changed. So, we will again calculate the cost function value, or then we will again update this cost function with respect to newly updated parameters values, and we will, based on that, we will again change these parameters, and it will, these iterations will go until your termination criteria is satisfied. So, we have already seen here alpha is the learning rate. So, learning rate generally we set as 0.01. Otherwise, if we want to make our algorithm learning this gradient descent method slow, so we will make this alpha value of this alpha very low, or if we want gradient descent algorithm to be fast, then we will take the high value, large value for alpha. So these are generally this is the range of alpha 0.001 to 1, and we can take any value between these if we are not having any idea. So then we can take randomly, but we do lots of experiment. So we generally take some low value, and then we try to increase value of alpha and then check what is the effect of value of alpha on the gradient descent algorithm, or the method, or how these parameter values are changing based on the value of alpha. So now there are three variations of gradient descent method. So there are three types of gradient descent. One is called as batch gradient descent, another is stochastic gradient descent, and the third one is mini batch gradient descent. So in case of batch gradient descent, what happens? We calculate the gradient of the cost function, and then we need to sum all training examples for each step. For example, let us go and see here. So when we are trying to update these parameters, so this is the gradient, that we calculated with respect to theta naught. So gradient of cost function with respect to theta naught. So here you see we are taking summation over I is equal to 1 to m. So if we are having m instances and we are taking summation over all these instances, so we are this is nothing but, you see, this is error term. So this error we are calculating for all the instances. So after updating these parameters, we are calculating the error for all the instances, and based on that we are updating the parameter again. So sometimes if number of instances are very large, so when we are calculating this term, it will be computationally very complex. So we try to reduce this computation, and how we can reduce it? To calculate this error over all the instances, we can reduce it if we calculate this error over few instances or only for one instance, and then based on this error we will update these theta. So there is one possibility that we are considering these errors for all the instances, and then we are using this error that we calculated for all the instances for updating these parameters. The second possibility is we will take only one instance for calculating this error. So this will be only for I is equal to 1, not from I is equal to 1 to m. So this error we will calculate only for I is equal to 1, means one-th instance, and based on that we will update our parameters, and then from the updated parameter again we will calculate error for the second instance, and that using that error again we will update our parameters. Then from the updated parameter we will calculate error on the third instance, and so on. So this will be fast, because in each and every step we are using only one instance to get this error term. And there is third possibility that if we are having lots of instances, we will make some small batches, like batch of 10 or batch of suppose 100 instances. So we will not calculate this error for all the instances, we will calculate this error for suppose batch of 10 instances. Then again for In the next step again we will calculate it for some randomly selected 10 instances and so on. So, based on these these three methods are there. So, in batch gradient descent we calculate this error term for all the instances. In stochastic gradient descent we randomly select one instance and then we try to find out error only for one instance, and based on that error we update our parameters. And in case of mini batch gradient descent we calculate this error for one small batch, mini batch, for example a batch of 10 instances or a batch of 100 instances, that we will need to decide based on the size of your data set. So, that we will need to decide based on the size of the data set. And so, these are three variations of the gradient descent methods. Here we can see these differences. For batch gradient descent you can see we calculate gradient of cost function and we need to sum all training examples in each step of updating these parameters. So, batch gradient descent is not good fit for large data sets, because if they are large data sets, in each and every step we will calculate error for all the instances, and these number of instances are very large. So, it will take lot of time, and so you can see here when we are calculating this gradient. So, here we are taking summation over I to n, where n is the number of instances, while in case of stochastic gradient descent we calculate the gradient only for one example, one training example at each iteration, and that example or instance we select randomly, and then using that error we try to update parameters, and then again in the next step we select one instance. Over that instance we predict the value of dependent variable, and then we check what is the error, and again using that error we will update our parameters. So, here you can see we have not taken summation. So, we are calculating this error only for the ith instance. So, that is only one instance that will be randomly selected. And in case of mini batch gradient descent we use some n samples instead of one, that we have done in case of stochastic gradient descent. So, here we take only n samples. So, we will need to decide the value of n. So, that is that n. So, if there are n instances in this batch, it is called a mini batch, because we are not using the whole data set. So, this whole data set is very large. So, we are taking a mini batch of this containing only n samples and we will calculate. So, you see here, so this I is equal to 1 to suppose 10. So, if we are taking mini batch size as 10, so we will calculate this error only for some randomly selected 10 instances, or we can do it sequentially also. So, in this lecture we have seen the gradient descent method for optimizing the values of model parameters, and that is nothing but we can say that we are using gradient descent method, we are trying to find out those values of parameters, model parameters, such that cost function, and that cost function in this case we have seen sum of squared error. So, sum of squared error or the cost function is minimum. So, using gradient descent method we are trying to find out model parameter values such that cost function value is minimum. And in the previous lecture we have seen another method, normal method, for finding these parameter values such that cost function is minimum. Here we have seen gradient descent method, this is iterative method, and there are three variations of these: batch gradient descent method, stochastic gradient descent method, and mini batch gradient descent method. So, now we will see another method for updating these parameters of the model. So, that is momentum update rule. So, in this momentum update rule, how we update these parameters? In this case, we have some velocity vector that we maintain, and this velocity vector accumulates gradients over time. So, in case of gradient descent method, what we have done, when we are updating these parameter values, we are considering only the current gradients, while in case of momentum update rule, when we are updating these parameters, we may accumulate previous gradients also, and then all these gradients will be used to update these parameters values. So, here there is a term that is velocity or momentum. So, Vt is the velocity or momentum at the tth iteration, and this momentum or velocity, how we are calculating. So, this formula is beta multiplied by Vt minus 1. So, you see this is the previous velocity at t minus 1th time or t minus 1th iteration, and beta is the momentum coefficient. So, generally this coefficient value is between 0 and 1, and commonly we take its value from around 0.9 or 0.99, but we can take its value low also from 0 to 1. So, generally we need to take experiment on this, and we find out what is the best value of beta in our case. So, we can say that this is one of the hyperparameter that we will use. We need to tune this hyperparameter value, means what is the best, we will find out during learning what is the best value of beta in our case. Vt minus 1 is the momentum or velocity at t minus 1th iteration, and then plus 1 minus beta and then gradient of this loss function. So, you see here gradient of loss function is used, but we are using previous velocity also, and in previous velocity, since this velocity is depending on the gradient. So, and that this velocity is having the term Vt minus 1 also, where Vt minus 1 will incorporate term gradient at t minus 1th instance and Vt minus 2 term also. So, that accumulates previous gradients also. So, in this way we can say that in momentum update rule, we are considering previous gradients or gradients over time, and so in this way we first of all calculate velocity, and then model parameters are, so model parameters here are called as weights, because in neural networks, that is again a machine learning techniques, and in that model parameters are called as weights. So, in general these parameters are written as Wt or weights, but these are nothing but that we have seen in the previous lectures, B0, B1 in case of simple linear regression. In case of multiple linear regression, we have seen theta naught, theta 1 and so on, or B0, B1 and so on. So, this W is nothing but B vector or theta vector. So, we are updating our parameters using this formula Wt is equal to Wt minus 1, means this was the previous parameter values, and we are now trying to update it by reducing neta Vt, where Vt is the velocity that contains gradients over time, and neta is learning rate. This is nothing but the learning rate. So, this formula you can relate with the gradient descent formula, where we update our parameters by using the formula parameter minus alpha into gradient. So, here gradient is nothing but the velocity, and velocity incorporates this gradients over time, and that is why this we can say this is the this accelerate the convergence process, or you can say very fast we may get the perfect values of these model parameters. So, now we can say that low momentum rate or that is close to 0, it means the update rely mostly on the current weight you see here. So, momentum rate is so this beta value, if this beta value is low, in that case this factor, so we are not using the previous gradients in to some extent, and if beta is close to 1, it means we are updating these model parameters depending on more on the past gradients, because in that case beta is close to 1. So, this term we are giving more weightage, and that is why we are giving we are updating our parameters based on previous or past gradients also. And so, in that case we can say it is providing more inertia and reducing oscillations. So, oscillations I just forget to discuss this, let us discuss it here. So, we have seen that the cost function in case of if this is the model parameters and this is the cost function, we are plotting this cost function like this, and this is basically you will get it parabolic curve. So, what happens, initially we randomly take some value of these parameters, and then using gradient descent method or momentum update method, we will update our parameters values. So, sometimes suppose initially these values were here, and so in that case this cost function value was this, and when we are changing it, so if learning rate is very high or momentum rate is very high, so in that case what can happen, the next value of W you may get here, and that is why you reach here, or you can say that the value of J was here, value of cost function was this much, and now the next value is this. So, and then again we changed it and we went here, again here. So, in this way we are so what we want if we are here, it means we are having some value of W. So, when we are updating it, so we should update this value such that we slowly go towards this minima. But what is happening if learning rate or momentum rate is very high, in that case we may have these type of oscillations, and we are basically ignoring, or we are losing this minima. We are oscillating only to the higher values of we are getting high cost values and corresponding W's. So, that to reduce that, to avoid this, what we do, we keep alpha or this neta, this learning rate we keep very low, or in case of this momentum rate also. So, in this way what will happen? So, there is we will in each different steps we will first get suppose randomly we were here, the value of W was here, and then we will change it here, then change it here. So, we will slowly change value of W, and finally we will get this W value such that this cost function is minimum. So, this is called as convergence. So, we want fast convergence, but we do not want oscillations. We want those values of parameters such that this cost function value for those parameters for that parameter values is minimum. And so if we will make learning rate very high, in that case we may not get minima, and we may oscillate in different values of parameters such that cost function value is always high. And if learning rate is very low, if we keep it very low, your convergence rate will be very slow, or you can say that your learning algorithm will take lot of time to find the actual value of parameters where cost function value is minimum. So we need to find out balance, some balance between these two values, so that our convergence rate is also fast, and we should not ignore the minima, and we should not always go in oscillations, we should avoid. So when to stop applying corrections means when we should stop updating these parameters. There may be different termination criteria. For example, one of the criteria is simply number of iterations. The second criteria may be when change in the cost function is very small. So cost function of in the function, cost function will be very small when it will be close to the minima. So we can also say that because when we see this graph, so this in this graph you see this here, the difference between cost function is very low, while here if we see, so cost difference between cost function is high. So when you will reach towards minima, your difference between the previous cost function value and the new cost function value will be, this difference will be low. So we can say that if when after in different iterations, so if in the next iteration we are getting the cost function value that is very close to the previous cost function value in the previous step, so we can assume that now we reached towards minima and we can stop there. So now this is the pros and cons of linear regression model, and we have already seen different assumptions. So first of the problem is we need to check all these assumptions, and then only we can apply linear regression model. And then the advantage of this is it can work on any size of data set. So if you are having large data set also, in that case also it will give you the information about relevant features in your model or in the data set. So in this lecture we have seen simple linear regression, and then how we can find out different parameter values of simple linear regression or multiple linear regression using gradient descent method or momentum update rule. We have already seen the another method for finding the best or optimized values of these parameters, that was the normal method, and we have seen today two more methods, that is gradient descent method and momentum update rule. So I am stopping here. In the next lecture we will see in detail multiple linear regression model. Thank you.